Okay, welcome to part 2 of the video. All right, so we're looking at this guy, and this H is down here. Now, this is in a plane. Okay, this is in a plane. In other words, they're all on the same plane. Now, the OH is coming at 90 degrees to the plane, and the BR is at 90 degrees to the plane. So I've drawn it like that, but if you could imagine it's like this. There's the plane, and the OH is on the top, and the BR is on the bottom. Does that make sense? Now, this is one of those things I said it wasn't going to be easy today. So that's the bit in the middle. That's the bit I've drawn there. Are we good with that? All right, there's an H here, isn't there? There's an H here. There's a C2H5 there, and there's carbons in the middle. Okay, are we okay with that? Are you still there? Things were... Yeah, it's hard, Janet, isn't it? Does anyone know the shape of this? What this is called? This is given a special name. I don't know if you know it, but I'll tell you anyway. This shape is known as... Oh, well done! Well done, Damani. How do you know this stuff? All right, it's not trigonal. It's trigonal. Trigonal bipyramidal. All right. Now, yeah, that's the name of it. Well done. It is exactly that. Trigonal bipyramidal. Okay. And that's the shape. Isn't it a beautiful shape? Right. Now, why am I bothering with the shape? Let me get rid of this. But well done, Tamani. You're great at this stuff, aren't you? Honestly. Maybe next lesson you can give the lesson. All right. Now, what happens is, anyway, so this thing becomes this thing. And then what happens now? Well, these electrons go onto there. And this is the beautiful thing. Let me draw it down here. All right, well, I think it's beautiful. You get the OH, okay, and there's the carbon. There's the hydrogen. There's the other hydrogen. And there's the C2H5. Now, can anyone, do you get what I've just tried to show you? Okay, do you get that? I hope you get it. What it is it's flipped, hasn't it? The whole stereochemistry has flipped. It's flipped like an umbrella on a windy day. Yeah, imagine I've got an umbrella. There's an umbrella. Okay, there's that. Oops. There's the umbrella. And on a windy day, what happens is it flips over the other side, doesn't it? It flips. Okay, and that's what's happened to this. The OH has gone on one side, the whole thing flips over, and it flips over there. Do you get that? Do you get that, everyone? Are we good? All right, now I'm going to try and do something that I don't know is going to work, guys, because you've been very good. I'm going to go to my chemistry notes and see if it's there. Yeah, it's there. Now, this is... oh, let me do something else. I'm going to show you a video, okay? I hope this works. All right. Now, this is SN2. All right. Oh, there. Well, that's working. God, it's a bit noisy. Now, I'm going to change the... I'm stopping presenting and I'm going to present again. Okay, so this mechanism, we're going to look at this mechanism because you've done very well. Here we go. Right, where is it? So there. First of all, can you see the University of Surrey? Can you see that? Excellent. Now, I hope you can get this, but we're going to watch a video. How long is it? It's about 2 minutes long. Okay, so this is the mechanism I've just tried to show you. Okay, here we go.
Primary halogenoalkanes undergo SN2 reactions, where the S denotes a substitution reaction. The N shows the reaction involves a nucleophile. 2 is the number of species involved in the slowest rate-determining step. A nucleophile is an electron pair donor. It is attracted towards species carrying a full or partial positive charge, with which it can form a dative covalent bond. Consider the reaction between a hydroxide ion in solution and bromoethane. Both reactants are involved in determining the rate of the reaction in a one-step process. The hydroxide ion attacks the carbon atom from the opposite side to the halogen atom, because the bromine atom, A, is so large it impedes the approach of the smaller hydroxide ion, and B, it repels the negative charge nucleophile. The lone electron pair on the nucleophile forms a new dative covalent bond with the partially charged carbon atom to give an unstable transition state complex. The complex behaves like an umbrella blowing inside out as the bonds rearrange into a tetrahedral structure. A bromide ion, called the leaving group, is released. The transition state complex.
Okay. Oh, there you go. Right, now, let's have a look. We go back to our stuff. Whoopsie daisy. Now, where are we? I've lost it. Oh, there it is. Okay. Did we understand that video? It's a beautiful video, isn't it? Now, don't forget, it's going to be on the video that I'm making now. But yeah, Tamani, it's not an easy thing, but don't worry about it. Obviously, as I've said like a million times, we're not going to be great at this, are we, over these holidays? This is just to introduce ideas to you. So when we get back to school, things are a lot quicker then. Okay? To be honest with you, most of the stuff we're doing here we'll have to repeat anyway, but we're going to do them much, much faster at school. Oh, don't worry about that. But forget that for now. Eh? I'll talk about that now. All right. But do you understand that it's basically what I was showing you in my very bad drawings? Okay, do you understand that? You understand something goes on, something goes off. Excellent. All right. Now let's talk about that bit, the bit that Timonis wants to know about. Why is it SN2? Okay, let's talk about that. Right, let me get rid of the umbrellas. Okay, there we go. Alrighty. Oh, I got rid of the wrong thing, didn't I? Never mind. Okay, I'm going to redraw it here. Oh, that's annoying. So this goes over there. You get OH. You get that. Hydrogen. You get the wedge. And you get that. Okay, what goes on here? Yeah, this C2H5. Okay, now what's this mechanism then? All right, what's it called? What's the mechanism called? Mechanism, what's it called? All right, well, first of all, you have the OH, and that is a nucleophile. So we call this nucleophilic, because the first thing is a nucleophile attacks my positive carbon there. That's the first thing that happens. So it's nucleophilic. The second thing is something is knocked out, and the thing that's knocked out over here is a bromine, or bromide, I should say. A bromide ion is knocked out. So it is nucleophilic substitution. Tamani, are you okay with that substitution? Are you good with that so far? Excellent. Okay, now let's have a look at this. Can you see how many things were involved in this? How many things were involved? Well, you've got the OH minus ion, and you've got this C3H7Br. Okay, there's two things involved there. Okay, one thing, two things. There's two things involved. Now, this is the slow part of the reaction, and the slow part of the reaction, and I don't know if you've done this, you may have done this already, this in your syllabus. The slow part of the reaction is known as the rate determining step. Have you done this? The RDS. Have you done that? Oh, you have done it. Okay, cool. So this is the rate determining step, and it's the slow part of the reaction. The slow part. Now, how many things are in the slow part? There's an OH minus and a whatever that is, this thing. Okay. So these two things because this is the slow part of the reaction, they're involved in the rate determining step. And that means they must appear, these two things, they must appear in something we call the rate equation. Does that make sense? Yeah, we're good there. Okay, so far so good, I think. They must appear in the rate equation. Well, what is the rate equation then? If those two things appear in the rate determining step, well, the rate is equal to the rate constant, K, times the OH minus ion, concentration of the OH minus ion, times the concentration of my halogenoalkane. Would you all agree with that? Because it's in the slow part, it must do. Tamani's good. Now, I'm asking you things that I don't know if you know about. What is the order of this reaction? What's the order of the reaction I've written there? Does anyone know what the order means? Oh, well done. It's seconds. Well done. It's second because this is OH minus to the power of 1. And this is C3H7Br to the power of 1. And 1 plus 1, order reaction is that one plus that one, okay, is equal to 2. So are you good with that? Tamani's good. Are the rest of you good with that? Are we good with that? Excellent. So, Tamani, it's pretty obvious now, isn't it? That because it's a nucleophilic substitution from here, yes, and it is order 2, this mechanism is known as an SN2 reaction. Are we good with that, Tamani? And the rest of you, are we good with that? Yeah, no, chemistry's cool, isn't it? It really can be cool. Really, it can be. But that's chemistry, guys. Chemistry's wonderful. It really is. Why do you think I do these videos? All right, because it's cool. It's a really nice subject, and it's all it's very logical. So it's called an SN2 reaction because of those things. All right, so there you go. Isn't that beautiful? All right, now, so this is an SN2. Okay, so now I'm going to go up and I'm going to do exactly the same thing, just to bore you senseless. Okay, now watch this. I can't remember exactly what I did here, but it doesn't matter. You get the idea. Okay, this is, what's this now? This is C2H5, and this is our Br. All right. Now, do you remember what we did already? We did it for a primary halogen-alkane, didn't we? So the mechanism is SN2 for a primary halogenoalkane, okay, which we've done, and which is the one I've drawn here. Now I'm going to change this halogen-alkane. I'm going to change it to a secondary. Okay, you watch how I do that. How can I change this to a secondary? Okay, I want to change this to a secondary halogenoalkane. I don't know if you can see this, guys. Halogenoalkane, but the writing is very stoppy-starty now. I think my internet's dying on me. I really do. So how do I change this to a secondary? Well, I replace one of the hydrogens here, and I'm going to replace it with a CH3. And now what's going to happen is, well, the same as before. The OH minus, let me do it in Y, the OH minus comes in here and that leaves. So for a primary, this is a very cheap way of drawing primary, and a secondary, the mechanism is SN2. Okay, it's the same mechanism for primary, same mechanism as for secondary. Okay, now I'm going to steal this. I'm going to copy it. I'm going to paste it down here. Okay, and I'm going to select it, I think. No, I'm not. I don't know what I'm going to do with it there. All right, let me select it if I can and move it around a bit. Yeah, the internet's dying. All right, here we go. Now, oh gosh, hurry up, machine. Oh, it is so slow. All right, oopsie daisy. Now there you go. So that's our secondary, and that's as I said, primary and secondary are both SN2. And now I'm gonna get rid of these words because it's confusing me. Now I want to change this into a tertiary. Okay, I'm going to change this guy into a tertiary. How do I change it into a tertiary? Well, I'm going to change it into a tertiary by getting rid of this and putting a CH3 here. And now this is a tertiary halogenoalkane. Okay, there's tertiary. All right, and now, and this is the interesting bit, or confusing bit, the OH minus ion here it is, it wants to get in this way, but the electron clouds of these guys, there's one methyl, the electron cloud of this thing, and the electron cloud of this thing, okay, it can't get through anymore. There's traffic in the way. It tries to attack my delta positive. Where's my delta positive? It tries to attack the delta positive, but it can't get through. Can you see there's stuff in the way? Can we see there's stuff in the way? It wants to go in, but there's stuff in the way. Are we happy with that? Are we good? Excellent. Well done, Lungi. Good, Janet. Right, now stuff in the way, if there's stuff in the way, when there's stuff in the way, there's things in the way, literally in the way, that's called steric hindrance. Okay, steric hindrance. To hinder means to prevent, or to prevent, or make harder, to make harder. Okay, so if there's someone in a doorway, they are hindering you from getting in. Does that make sense? Are we good there? Okay, Janet, Longy, Tamani, you're right, yeah. So this, in chemistry, when things get in the way, it's known as steric hindrance, okay? So that means, unfortunately, that the OH can't get in. So for tertiary halogenoalkanes, the mechanism cannot be SN2, okay? There's another mechanism. And now in the last 5 minutes or so, let's try and do the last mechanism. And I'm rushing a bit, guys, I'm afraid, because I realize the time is killing us a bit. So now let's have a look at this. This is a C. This is our bromine. Okay, now we've got a methyl. We've got another methyl. And we've got another methyl. This is a tertiary halogenoalkane because it's got 3 methyls attached to that carbon. Now, the OH minus is here. Oops, let me do a different color. The OH minus is here, but it doesn't do anything because it can't attack. So what happens is these jump onto that on their own. Okay, and what do we get? We get this. We get a C, CH3, 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 positive because it's heterolytic bond efficient, and the Br breaks off. And there's my Br minus. Now these electrons, sorry, let me redraw this somewhere else. That jumps off, the Br comes off on its own, and then what happens? Well, the OH minus ion attacks what's left. Okay, and what do we get? We get the product, which is, so let me draw it down here, C, CH3, oh gosh, my internet is dying, CH3, CH3, OH. Okay, so that's what happens with the tertiary. Now, Tertiary happens because of this thing called steric hindrance. So you get this thing in the middle, and this thing in the middle is known as a carbocation, because it's a cation, because it's positively charged, and it's a kind of an organic species, so we call them carbocations. All right. Now, what's this mechanism? Well, once again, it is nucleophilic substitution. It is a nucleophilic substitution reaction. So it's going to be called SN. But in this case, one species, there's only one species which is in the rate determining step. So the rate equation for this would be R equals rate constant